Good evening and welcome to Everything Matters, Tales from the Periodic Table. Tonight, the sixth element, carbon. Beginning on carbon, we're all familiar with the Great Periodic Table. We had a really great talk last month from Paul Stepahin about the periodic table. And by the way, this periodic table you can find at periodictable.com, obviously. We're going to today look at the sixth element up there, carbon. In this form, you see, it's just showing a diamond here, but carbon has lots of forms that we are familiar with. Historically, carbon has been known, well, it's been known prehistorically, because this form of carbon has been known for many thousands of years, coal. And actually, you can still buy coal, but there's only one place in California you can buy it. And just coincidentally, it was in Brisbane, so it actually was really easy for me to drive and get a chunk of coal for you tonight. It's a company that you see right down to Lazari. And they don't sell a lot of coal. They sell mostly charcoal and wood chip stuff, but they do sell a little bit of coal in California still, because we're not a big coal burner here in California. So coal is one of the forms that's been known historically. The other one that's been known historically are diamonds. So those two forms are really are prehistoric almost, before written language, and they've been known for a long time. The first carbon that we know as an element that was declared an element was declared by the father of chemistry here, Lavoisier, and he was the one who recognized carbon as an actual element, something that doesn't break down into other forms, and that was in the late 1700s. Carbon has an atom that's a little bit bigger than hydrogen. Just wanted to give you some scale for how big carbon is. It's about twice the size of a hydrogen atom. And if you feel the density of carbon, it's about twice the density of water, about 2 grams per cubic centimeter. But if I had a big chunk of diamond here, which I don't, that would have about 1.5 times the density of graphite, or coal, so about 3.5 grams per cubic centimeter. Remember that water is at 1 gram per cubic centimeter, and there's a bunch of other things. If you want some comparisons, steel is about 7 or 8 grams per cubic centimeter, and if you can work your way up to gold at about 19 grams per cubic centimeter, and osmium, the most dense element, we won't get to that one for a long time, and I don't think I can have a chunk of that. It's a little too expensive at 22. The winner at 22.5 grams per cubic centimeter is osmium. Graphite, carbon, because it has many forms, has different hardnesses, depending on what form you find it in. If you find it in the graphite form, in this coal form, it's actually pretty soft. It's one of the softest elements you see at a Mohs scale of hardness, named after Mohs. Graphite is really a very, very soft material at a hardness of about 1.5, and at the bottom of the scale you have the other form of carbon, diamond, at 10, the hardest substance known. So we have a big range there for the hardness of this element. It comes in, as I mentioned, the different forms. We've talked about 2 forms here. We have the diamond form. I have some little diamonds in here, very tiny diamonds, and the coal. But there's lots of different forms that carbon can link up in, because it's so polyamorous. Where's Melissa? There you are. Okay. Are you happy I'm using that word? It has lots of ways to bond with itself and other elements. That with itself it can bond in these ways. In the top row, for instance, the first one on the left is diamond. The second one in the middle there, that one's graphite. It's in sheets, which is why a pencil is, when you write with a pencil, they just kind of slough off as you write with the pencil, because they're not very well bonded. The layers between each layer is not very well bonded. The third one is just a mineral. The middle row, those are bonded in a 3-dimensional structure. Those are called fullerenes, and we'll get to that. And the bottom row, there's one that's just amorphous carbon. It's just randomly bonded. And then we have carbon nanotubes. The graphene that we're going to look at tonight is more like the graphite at the very top middle row. So those are called allotropes, different forms of the same element. I have here, this is a little bag. If you come up and see this after, this is another form of graphite here that's man-made. These are man-made layers of, I'll take it out of the bag so we can put it up on the screen here. Jim can get a close-up shot of this. This is called, well, I don't know if, guess what? It's black. It's made, this is very thin, and this is built up by layering layers of carbon one on top of the other. So this is kind of crystalline like graphite, but it's much more orderly structured than graphite is. It's called pyrolytic graphite. Actually, magnets repel this stuff. It's really quite interesting stuff. Pyrolytic graphite. So we have these two forms. Again, we talked about the allotropes, graphite and diamond. This is what a diamond looks like if it's in the rough before it's been faceted and polished. It has kind of a octahedral structure, 8 faces, all triangles, one of the platonic solids. If a low-grade diamond would look something like this, colored, kind of, this one's kind of, I guess these have become more popular lately, these chocolatey colored ones. But you can also make them. You don't have to dig them out of the ground. You can make diamonds. These are industrial-grade diamonds that have been manufactured. These are sand grain size industrial diamonds, and these you might use as an abrasive in industrial processes. Natural diamonds are taken out of the earth, and in a few places, not many places, mostly in Africa, and there's some large deposits in Russia as well, though. Of course, they're all controlled by the De Beers company, at least the ones that come out of Africa, which makes them so expensive, because they actually shouldn't be very expensive at all, if you look at the rarity of them. The last row, carbon nanotubes, that other allotrope, if you actually had a bottle of them, they would sort of look like this. It's just a pile of carbon, it looks like, but those are actually nanotubes. Actually, I have the spherical ones. These are this is, I don't know if you can see this, Jim, but this is 5 grams of, well, that black powder there's actually spheres. So those are spheres. It's just a black powder, really. I mean, because they're spheres of 60 atom spheres. You're not going to be able to see that with your naked eye or any microscope that's ever been invented, except for maybe the force microscopes. But those are buckyballs, which we'll get to. As a matter of fact, let me just show you that. Here's the Buckminster Fuller. It was named after Buckminster Fuller. These are called fullerenes. And that's called Buckminster Fullerene, because Buckminster Fuller kind of made popular the geodesic dome, which this kind of looks like. So carbon, being polyamorous, has a lot of ways to bond chemically. It has 4 possible places, 4 electrons that are sort of waiting to be shared in its outer shell. And so you can share those with anything. Like, for instance, you could share them with hydrogen atoms, and 1 hydrogen atom per connection. And now you have a carbon and 4 hydrogens. You have CH4, which we also know as methane, which is, of course, what comes out of your stove, and it's flammable. You could also have a carbon atom. Let's kind of bend 2 of those bonds over and attach an oxygen to them, and you have what? CO2, carbon dioxide, which we're going to talk about tonight. Laurie's going to talk about carbon dioxide. But you can also bond all kinds of things. You can bond them into chains and get all these chemicals, propane, butane, octane. You can get alcohols and sugars out of it by bonding various elements. You can get acids and amino acids. Carbon bonds amazingly numerous ways. There are over 10 million ways, 10 million chemicals that contain carbon in them. There's a whole branch of chemistry, organic chemistry. 10 million of them. Over 10 million of them. Now, if we look at how common carbon is, it's actually a very common element. We know that hydrogen and helium in the universe are very common. Carbon is the 4th most common element after oxygen: hydrogen, helium, oxygen, and carbon. So carbon makes up, I have to look down here because I haven't memorized these numbers, 0.5% of the atoms in the universe. They are actually made inside of stars. You can see here the carbon is made in both large and small stars. I'm going to go back 1 slide because I want to look at some of the other percentages. In the solar system, it's also the 4th most abundant element, but if you look in the oceans, it's not actually a very abundant element in the oceans, but in the human body, it's like the 2nd most abundant thing. 18% of your body is carbon. So it has lots of different abundances depending on where you look. But as far as the entire universe goes, about the 4th most abundant element. carbon formed, as I was saying, it's formed in stars, but it's also used in stars as part of the cycle that turns hydrogen into helium. That's that fusion process that produces the energy that we experience from the sun. And that cycle that carbon participates in is called the CNO, carbon, nitrogen, oxygen cycle. And I just wanted to go through that because it's actually kind of cool. You start with a carbon atom, a carbon-12 atom, the most common atom. We'll get to that in a little bit. Carbon-12 has 6 protons and 6 neutrons in the nucleus, and you smash a hydrogen atom into it, the red one there. And what you get out of that is you get a nitrogen atom and a gamma ray. And the gamma ray is energy that flows out. So the gamma ray provides energy with that part of the reaction. So we've taken carbon and we've made it into nitrogen, nitrogen-13. Now we take that nitrogen atom and it's radioactive. It decays, and it decays into a carbon-13 atom, different isotope of carbon, and it gives off a positron, and that's energy. So we're still making energy here. So now we have carbon-13, started with carbon-12, now we have carbon-13. Let's take the carbon-13 atom, smash a hydrogen atom into it. We're going to make nitrogen again, except now we're not making nitrogen-13, we're making nitrogen-14, and a gamma ray. Take that nitrogen-14, yeah, it's going to go on for a while here. Take that nitrogen-14 atom, we're going to smash a hydrogen atom into it, and produce oxygen, oxygen-15. Take that oxygen-15 atom, it's radioactive, so it decays and produces energy. Now into nitrogen-15, different nitrogen, and now finally getting down to the bottom here, we're going to take that nitrogen-15 molecule, we're going to smash in one more hydrogen atom into it and create carbon-12. So we've now started with a carbon-12 atom, we've added 1, 2, 3, 4 hydrogen atoms. We create a carbon-12 atom and a helium atom at the end. So we changed 4 hydrogen atoms into a helium atom, and we're left with a carbon-12. So the carbon is really a catalyst here. It just helps in the chemical reaction. So I was mentioning all these different numbers above the elements, the 12s and the 13s. Those are isotopes. Carbon has 2 naturally occurring stable isotopes. Carbon-12, which is most of it, 98.9%, and carbon-13, about 1.1% of all the carbon is carbon-13. Oh, thank you for that. Can you hear me coughing? Thank you. Much better. There's one unstable element of carbon that we're all familiar with. It's not carbon-12, it's not carbon-13, it's carbon-14. Carbon-14, 6 protons, 8 neutrons. It's 1 in a trillion atoms of carbon on the Earth. 1 in a trillion, not very many. It's radioactive, so it decays. It decays by shooting an electron out and becoming nitrogen. It's the nitrogen in our atmosphere is the same kind of nitrogen. Now, it's radioactive, it decays, it takes a certain time to do that. How much time does that take? Well, there's a guy that measured that. The first guy to measure that really accurately was this guy, Willard Libby, in 1949, and he determined that it takes for half of that carbon to decay, takes 5,568 years. Well, that's not a lot of time in the geologic sense. I mean, the Earth's been around for 4.5 billion years. Wouldn't all the carbon have decayed by now? I mean, that's, almost 1 million half-lives since the Earth was formed. There should be no carbon-14 at all on the Earth. Where does it come from? It's actually manufactured high up in the atmosphere. Cosmic rays come down into our atmosphere and hit nitrogen molecules, and actually they change the nitrogen-14 into carbon-14. And then that carbon combines with oxygen, forms carbon dioxide, which is used by plants, and the plants are eaten by the animals. The carbon dioxide dissolves in the water. And so this is a constant supply of carbon-14 that's being made in our atmosphere. So you are subject to a constant supply of carbon-14 all the time. You eat a constant amount of it all the time. And so you have a constant amount of carbon-14 in you. I'm going to skip the next slide here because we already talked about that. if you have a constant amount of carbon-14 in you, the only way to change that is for you to stop absorbing carbon-14. And the only way for you to stop absorbing carbon-14 is to die. When you die, the carbon-14 inside of your body starts to decay, and you have less and less and less carbon-14. After 5,568 years, half of it is left. So if we started, let's just throw out a random number with 1,024 atoms. After 5,568 years, how many would be left? Half as many, so there'd be 512 atoms left of carbon-14. After another 5,568 years, how many would be left? Half of that. So half of 512, there'd be 256 atoms. And after another half-life, 256. After another half-life, 128, 64, 32, 16, 8, 4, 2, and after 10 half-lives, 1 atom would be left. In the next 5,568 years, there's a 50-50 chance that that atom would decay. But you can see that after 10 half-lives, you have about 1,000th what you had to start with. That's a good number to remember. 10 half-lives, 1/1,000th left. So if you have your body in a casket, or you find an ancient site where they had a barbecue in their Weber, and the charcoal is still there, you could measure the amount of carbon-14 left. And as a matter, this is how you would do it. You would measure the amount of carbon there. If you count up all the carbon, you can count up the number of atoms of carbon that there are in the barbecue. Then what you do is you measure how much radioactivity is coming from that barbecue, and that lets you determine the number of carbon-14 atoms left. And by knowing the number of carbon-12 and the number of carbon-14, you can determine how old that barbecue was. And it's good out to about, not quite 10 half-lives, but about 50,000 years is carbon dating is good too. So, oops, there we go. That's the last one I wanted to do. So what are some of the other applications other than dating anthropological sites? What else can you do, or archaeological sites? What can you do? Well, I have an example right here. This is a result of a fellow who puts out 98% perspiration and 2% inspiration, Thomas Alva Edison. This actually is the kind of filament that he produced. It's a carbon filament. He found out that carbon can actually last a long time. It doesn't vaporize. It'll last for an extended amount of time. And that was all the filaments that he produced. We now use tungsten. It has an even higher melting point than carbon does. So, carbon filament, Thomas Alva Edison. You can also use it in projectors. If you strike an arc between two carbon rods, it'll make a really bright arc between the two rods with electricity jumping from one rod to the other. And that bright white light is from the carbon glowing. If I lit a candle here, which I can't do, the candle would glow yellow, and that yellow is actually carbon that's very hot and glowing yellow hot. It's solid pieces of carbon. And actually, if you try this at home, take a candle and light it, and put a piece of metal above it, or a spoon or something like that, and you collect soot up here. That soot is actually, that proves to you there was carbon in the flame, but also it's a good way to produce those buckyballs and the nanotubes. Of course, graphite is used in pencils, and here you can see a large chunk of graphite that's been sawn up there, and then they put the graphite in the middle of the wood and glue the wood together, and you get pencils. Carbon fibers can be formed, and you can put those carbon fibers, weave them into a cloth, put that cloth into an epoxy resin, wrap it around things, and make very light, very strong carbon fibers, very strong, stronger than steel, but it's also a lot lighter than steel. So this is an industrial process that's used in a lot of places to make airplanes, boats, bicycles, very light and very, very strong structures. That's all I have right now. I'd like to thank you all for coming. We're going to move into our next segment now, and thank you for coming.